So, okay, with that in mind, let's pick a solution that does a couple things. So maybe let's pick a solution that lets us enforce maybe the first three of these, which we would need three unknown coefficients to do that. So our unknown coefficients equation would be something like u over u infinity is equal to a plus b y over delta m plus c y over delta m squared. So that's our polynomial. This is the velocity profile we're going to try, we're going to assume is the right answer. And again, like we make this assumption, we go through, solve the math. The answers we get depend on how accurate this was to begin with. And we have really no way of checking that. We just have to sort of force it to be true, and then you'd have to check it with some other method. So let's go ahead with this example. So there's our equation tiny up in the right-hand corner. What we're going to do then is start enforcing conditions on this to match our profile. So the first thing we're going to do is let's pick the first condition. This is no slip. And again, this was saying u at y equals 0 equals 0. So to enforce that, let's take our equation. This would be u over u infinity is equal to, we want that to be 0, right? And then we're going to say a plus b y over delta m plus c y over delta m squared. And then we evaluate that whole thing at y equals 0. So if we do that, so at y equals 0, we get back this term goes away, this term goes away. So we just get back that a has to equal 0. Makes sense, right? We have this velocity profile at y equals 0. We can't have anything left over. So a has to be 0. Okay? So that's the first condition that ensures no slip. Second condition, what do we want to do here? So let's say we want u at y equals delta m to equal u infinity. We want our velocity at the edge of the boundary layer to be recovered. So again, we do the same thing. Now we use our slightly simplified equation. We're going to say u over u infinity is equal to b times y over delta m plus c y over delta m squared. Delta m whole thing squared. So evaluating this would be u over u infinity. To be u infinity would be 1. Right, so the left-hand side is 1 is equal to b times 1 plus c times 1 squared. So this tells us that b plus c has to equal 1. Okay, so this makes sure that the velocity is recovered at the outer edge of the boundary layer. Okay, so we need one more thing. The one more thing that let's do here would be let's recover shear stress at the edge of the boundary layer. This one is so tau at y equals delta m is 0, right? And tau is again defined as mu partial u with respect to y, evaluated at now we're at y equals delta m. So we're forcing the shear stress at y equals delta m to be 0. So what do we do here? I guess let's take that definition of shear stress. You see in this definition of shear stress, u, right? U appears here. So that's great. We have an expression for u, so we can evaluate this. We take our expression for u and plug it in here. That looks like this. It would be, where are we here? So plugging it in, it would be mu times partial with respect to y of u infinity times b y over delta m plus c y over delta m squared. all of that evaluated at y equals delta m. That has to equal 0. So simplifying this, it becomes b over delta m plus 2c over delta m is equal to 0, or b plus 2c is equal to 0. All right, I just took the derivative here. Yeah, derivative here with respect to y, that became this. And simplified down to b plus 2. So we have two equations, two unknowns. If you solve this system of equations, you find b is equal to 2 and c is equal to minus 1. So that yields our final velocity profile, which is u over u infinity is equal to 2y over delta m minus y over delta m squared. So this is the velocity profile that happens to enforce the three things that we chose as important. Now, you don't have to choose these three things, right? If you have some other condition or something else is important to you, you can choose other things. If you choose other things, your answer changes here, right? So this answer is specific to these assumptions or these conditions. Questions? Okay. Great. So we have our velocity profile. Now we have to actually go and plug it into the integral equation and see what happens there. Here's what we did. I guess if you wanted to shortcut this process in the future, what you would end up with is, let's see, zoom in a little bit. So if we had made the assumption that the velocity profile was linear, like as shown in the top row there, we would have ended up with that velocity profile. So we would just, enforcing the conditions, we would end up with that velocity profile. But what this table is assuming is that we're enforcing the conditions in the order that I told you, right? The 1 through 4. Again, you choose a different condition to enforce, you get a different answer from the table. So keep that in mind. But I think generally speaking, people like to enforce in this order of priority. So these are commonly used, and it shows up here. So we did the second order polynomial. Why is it different? So like where did this whole thing come from? Well, you see our velocity profile here. This is the one we solved for. This whole thing here comes along because this is a general solution for the case where you have shear-driven flow or you have velocity injection. So if you don't throw those things away, you carry that along. Same thing would go for the third order polynomial. And you can start to see where it just becomes a big pain in the ass to deal with. Right? But you can do it, right? You might even use Maple to do it or something like that. So, okay, this is available, but keep in mind the assumptions that go into it. What do the assumed velocity profiles look like, by the way? So here's the velocity profile we chose, the quadratic one. The actual, or like let's say for this solution where you have just a conventional boundary layer, no injection, not shear driven, what does that look like? Well, the dotted line is the, we'll call the accurate solution. It's the Blasius solution. The Blasius solution is an analytical solution to this problem based on the conservation of momentum equations. But it is developed for this limited case, and it's an exact solution. So that's the accurate one. That's kind of our benchmark. If we were to assume a linear profile, that's this one here. So you can see, we're enforcing no slip. We're enforcing, I guess, recovery of u infinity at the edge of the boundary layer. But within this, there's some error. And is that important? I don't know. I guess it kind of depends, right? But you can get maybe a pretty decent answer with a linear profile. You're going to have error because if, let's say, you want to predict the shear stress. What is the shear stress, or how do you compute the shear stress? That's the gradient of this velocity profile at the surface. So there's a difference in the gradient at the surface. So that's your error, right? Likewise, I guess you could go to these higher order ones. So our quadratic one is, second order one is here. There's still a bit of error, but it's better, quite a bit better. Third order, you're really closely tracking. There's still error. So you could go as far as you want on that, but you can kind of at least understand what the benchmark is there.